you guys hear me?
Yes.
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 All right, good. Let's see, start video. Damn it, to mute everybody. Oh, there it is. Okay. All right, everybody should be muted now. Okay, the UI for Zoom is weird. Like, at least on my computer, it's like instead of being one single, I don't know what you'd call it, but like, so, like software window, there's like 5 windows. They just seem to pop up everywhere. It just takes me a while to find it. All right. Okay, so last session, we were dealing with heat curves, and we will continue on that path right now. Okay. Yeah, let's see. Let me just grab this real fast from the other. So the most important things for solving just kind of quantitatively plugging through these types of problems is this set of equations.
Dr. Dragna, we can't see your screen.
I heard a voice in my head. Oh, my screen sharing paused. God, why does it keep doing that? Resume share. Also, my headset is not connected. Okay, I think I'm good now. All right, y'all can see the screen and hear me, correct?
Yes.
Okay. Also, can you make it horizontal? Yes. It doesn't help if I zoom out, does it? Switch to these. Okay, I think that fixes it. 10 minutes as opposed to 20 minutes of technical problems, so getting better. Let's see. This is the problem now. Hold on. I'm not sure I can hear you guys, but it doesn't matter. I guess if you need to, just type something in the chat box. I'm not sure what. I have like 18 different speakers in here, and I can't tell which one it's playing through. But as long as you guys can hear me and I can read what you're asking, I think we'll be good. Okay. So yeah. So in this problem, and these types of general problems, what we're looking at typically is, or at least in this specific problem, we're looking at how much heat it's required to take an ice cube all the way through a bunch of phase transitions into steam. And we're going between 2 different temperature ranges. And so it's what you end up doing here is you end up just doing multiple different calculations as you switch between phases and you go through the phase transition. So there's a lot to think about in terms of like what's happening physically. And we kind of got into that last session, like you can draw these Boltzmann distributions and think about why the phase transition's flat and stuff. But from a quantitative perspective, it's somewhat straightforward to do once you kind of get into it. So these little, I'll just delete those. So the main thing is when you're going from, let's say, like the way to break it up, I guess, inside of your mind is exactly how it's broken up on the heat curve. So like, let's say that you were given this problem, but you weren't given a heat curve. The heat curve is like a really handy tool to kind of draw out to break up the different processes to understand how you're going to have to calculate the heat at each point. So each leg of this, from here to here, let's say, I'm just going to do them in different colors, and then from there to there, uh, and there to there. Each one of those is going to require its own little separate calculation. But the calculations that you end up doing are similar for each one. So it's not like there's some separate equation you have to whip out for each of these. You just got to make sure that you're plugging in the right values there. And so for when you're not at a phase transition, all the energy that goes into the system, so all the heat that goes into the system, is going into increasing the kinetic energy of whatever phase you're in. In other words, it's going into increasing the temperature. We use those words somewhat interchangeably. So when you're not at a phase transition, that's what you're looking at. And so the equation you want to use for that is Q is equal to C sub P times delta T. And M is the mass. M is the mass. C sub P is whatever the heat capacity is, or the specific heat capacity, I think. And delta T is equal to the final temperature minus the initial temperature. Delta always means that, finus minus initial. So if we wanted to write that out in plain language, we'd say temperature change. And then when you're at the phase transition, so if you're at a phase transition, there we want to use Q is equal to delta H times N, where delta H, this is going to be the enthalpy. I don't know exactly what like the general term is it for it, but it's the enthalpy of like melting, or the enthalpy of freezing. It's like the enthalpy of the phase transition. And then N, this is just the number of moles. And sometimes, I think I talked about this before, but sometimes you'll see it'll be, if delta H, the enthalpy of the phase transition, it'll either have units of energy per unit mole or energy unit per mass. If it's energy per unit mass, then the N is no longer the number of moles. You would use mass instead. So you just got to be careful of that. Okay, but yeah, so using these two equations, though, we can go back and apply that to the heat curve. So at any of ice, liquid, or gas, we're going to be using this equation here. But at the phase transition, where we're going through melting, or we're going to vaporize things, we're going to be using this equation here. And so if we wanted to write this out, we have this, the general problem is that we're going from minus 20 degrees Celsius at atmospheric pressure to 150 degrees Celsius at atmospheric pressure. And so the way this would end up looking, if we tried to write an entire equation for it, would be you'd want to break it the way I think about it is that you break it up in terms of what's happening at the temperature, at these distinct temperature changes. So the phase transitions, because this is water, if it wasn't, I guess for water, the assumption is, you know that at atmospheric pressure, it's 0 degrees Celsius and 100 degrees Celsius for freezing and boiling, respectively. But the phase transitions here are 0 degrees. This is where it's going to go through melting. And then 100 degrees Celsius, which is where it's going to go through boiling. We use the terms, fusion for melting and vaporization for boiling, but it's the same thing. And so those are the kind of way you want to break things up. So the way you want to kind of think about it is I'm going from minus 20 degrees to 0 degrees Celsius. That's one calculation. Then at 0 degrees Celsius, I'm melting. That's another calculation that we're going to do. And then as I get above that, as I go from, let's see, wait, what did I do here? Minus 20, oh yeah, because we're in Celsius. Sorry, I'm thinking in terms of Kelvin. As we go from 0 degrees Celsius all the way up to 100 degrees Celsius, that's another calculation. And then I'm going to go from 100 degrees Celsius. I'm going to go from 100 degrees Celsius to 150 degrees Celsius. And that's another calculation. Wait, I messed up here. Hold on. I left out one of them. At 100 degrees Celsius, we're going to be going through boiling. And so each one of these is going to require a separate, we'll call that 1, 2, 3, 4, 5. So each of these things corresponds to a separate calculation. There's still someone in the waiting room? Did I screw up? I don't even know if I have a waiting room. I don't even know if I have a waiting room. As Newton's allow precision unmuting themselves. Yeah, I didn't even know I had a waiting room. I don't even have a waiting room enabled. They might be in the, tell them to go on, they might be on the wrong Zoom meeting. Sorry, I'm reading the chat box here. It says someone's in the waiting room. Yeah, tell them, that's the problem that I had. I was on the UT Zoom, but I wasn't using my UT like login. Like I had created a separate, I created a separate account for my UTexas email, but didn't log in through like the secure way that the university does. I don't know. There's some technical rigmarole there. Yeah, what that guy said. Yeah, you have to log into the SSO in the app. And then that fixes everything. Otherwise, you're on the basic plan. I don't know. That was confusing for me as well. Am I recording this? Yes. Okay, good. Okay, so we have this 5 steps here. And if we were to draw the heat curve for this, we would see, like that's kind of what I think of the heat curve is. It's sort of a crib sheet that sort of helps with the bookkeeping for this. So this would correspond to process 1. This would correspond to process 2. This would correspond to process 3. This would correspond to process 4. And this would correspond to process 5. So from here to here, I'm just taking an ice cube and I'm heating it from minus 20 to 0 degrees Celsius. Then at process 2, I'm looking at the phase transition of melting, and then I continue to heat it up. So now it's melted though, so now I'm looking at liquid water and how that heats, which heats, the way the temperature changes just changes differently. And then at 4, I'm going through another phase transition. So that's a different calculation. And then finally, when I get to steam, I'm just looking at how that changes temperature with respect to how much heat goes into it to change it from one temperature to another. So once you get this set up, though, it becomes just a series of calculations that you have to do. So let me back out to my other notes real quick and grab some useful information here. So we want this. I don't really want to cut that. I just want to copy that. So we need that. And we need this. So in order to do these calculations, let me zoom out a little bit. In order to do these calculations at these different steps, the 2 components you need are, the 2 components that you're going to need are the heat capacities for when I'm not at a phase change. So this is what we use when we're not at a phase change. And then we also need the delta H's, the enthalpy associated with each of the phase change. So this is for when we're at the phase change. So these are sort of the tabulated values that you need in order to do the different calculations here. So I want to shrink this down a little bit. It will not let me because it's a picture. There we go. Phase change. Let's delete that. And then so we're using this when we're not at a phase change. So yeah, there's no, the heat capacities are what we're looking at for this not at phase change. So C sub P is the heat capacity. At a phase change, in a sense, I think this is on the practice worksheet, people will say that the heat capacity becomes infinite, which is not really true. But you kind of get the idea because the slope becomes 0 at that point. But let me avoid getting distracted by kind of going down a path of explaining something really conceptual here. And let's bang out this calculation here. So at step 1, we're looking at this part. And so we're saying, okay, I'm just going from minus 20 to 0 degrees Celsius. And I want to use Q is equal to M times C sub P delta T. So the main thing, the important thing here is that, or the thing that changes with each of these calculations is delta T and which heat capacity you use. So you want to make sure you use the appropriate heat capacity. Sorry, so we're using, for this whole thing, I want to say we have 100 grams of H2O. That's important too. Well, heat capacity and enthalpy broad rate. Oh, no, you definitely don't have to memorize the heat capacities. At least I don't have them memorized, so I wouldn't bother with that. You might accidentally memorize the one from water because we just go through it a lot, but yeah, usually I'm trying to think of where there's an exception to this. Usually these kind of tabulated numerical values in physical chemistry you don't have to memorize. I guess some like really specific ones you need to know are like and maybe we even give you these, I can't remember, but like the ideal gas constants and things like that. I don't think that'll come up on this exam, but I guess I'll put it this way. If there's some numerical value that you have to memorize, I'll let you know. Also, this class is online and it's the exams. I know we haven't given you a lot of details. They're going to be open notes, open world kind of thing, with the exception of maybe talking to your friends. So you can always look this stuff up. All right. So yeah, so we'll give you the heat capacity. So then we're just looking to do these calculations. And so for part 1, Q would be equal to the mass times the heat capacity of liquid water times whatever the change in temperature is. So at this point, it's pretty much solved. It's 100 grams. And then we come in and we want to take this. It's 4.184 joules per gram degrees Celsius. And then the temperature change is going to be the final temperature, which is 0, minus the initial temperature, which is 20 degrees Celsius. And then you would just calculate this out and you get some number for it, which I'm not going to bother doing. But you can see your units cancel out and you're left with joules. So you should be left with joules. Why is the heat capacity of liquid not solid? Excellent question. That's because I made a mistake. Because we are in the solid state right now. Sorry, guys. Okay. So then we get into the second leg of this, which is we're at the phase transition. Okay, so here, there is we don't really think about this in terms of heat capacity. Now we just use the other equation, which is just that Q is equal to delta H times N. And this problem actually gives a good one because it gets at what I was saying before, which is that it's not always N, it's not always the number of moles. It's sort of dictated by what the units are on the delta H's that you're given. So here you'll see that delta H fusion, delta H of fusion, that's the one we're looking at right now, right? Melting, yeah. Here we're looking at delta H of fusion, and we see that it's in grams. Canvas real quick, actually. Give me 1 second here. Okay, sorry. All right, so yeah, so here we're in here we're in grams for delta H of fusion. So we're not going to use N. Oops. We're not going to use N here. We're going to use M. So the number that you should come out with, and let me actually just do the calculation because I think that'll make it clear. The number you should come out with should be in terms of just joules or kilocalories or whatever the problem's in. It shouldn't have any kind of units on it like grams. Okay. Y'all are ahead of me on this. So yeah, so what are we looking at here? You want to make sure you're using the delta H that is, you want to make sure you're using the delta H and you want to make sure you have the proper sign on it. So delta H of fusion is 334 joules per gram. Fusion is just a fancy word that people use for melting, just to make it more confusing. So we just plug this in per grams. And then we don't have number of moles again, right? You want to use a number of moles here because in the denominator here, we have grams. So the units that you want to cancel out are actually grams. If your delta H of fusion, this tabulated value that you have, if this tabulated value that you have is given in terms of joules per mole, then you just use moles. So the units in the denominator of delta H dictate which you multiply times. It's not always just the number of moles. And it's easier here, at least quantitatively, because we don't have to do any conversions to just have it in grams already. And then, this equals whatever. This one's actually easy. You can do it in your head. But yeah, this also equals some number. I'll leave it up to you guys to do the math here. Okay, so one thing to note here though is the delta H of fusion is 334 joules per gram. The delta H of, if we were to have another delta H in here, we don't necessarily have to give this to you, but the delta H of freezing, if you want to think about it, that is the inverse. It's not the inverse, it's the negative of that. So when you go back, and because these processes are reversible, all right, I can't do that. Because this process is reversible, when you go back and forth between them, all you do is change the sign. So for the forward process and the reverse process, you can just flip the sign on delta H. So the delta H associated with melting 100 grams of water is whatever this number comes out to be. I'll just write it out. It's 33,400 joules. That's the energy associated with melting, the endothermic process, which is what you'd expect it to be a positive number. If we go in the reverse direction, it's the same magnitude, it's just now negative because now you have an exothermic process. Yeah, you should come out with joules because we're talking about energy. Energy is expressed in terms of joules. Celsius is a measure of temperature. So you should always come out taking care of units, especially in these introductory like physics and chemistry classes, can save you. Even if you have no idea what the hell you're doing on an exam, you can pay attention to your units and just kind of sometimes accidentally get the right answer by multiplying things. That was my experience as an undergraduate. So pay close attention to the units. They feel extraneous, but they're really not. Okay, so then we go to process 3 here. And now you'll start to get some feeling of what I'm saying, where it's just kind of the same thing over and over again. So here, Q again is going to be equal to M times C sub P, but now we actually do use the liquid one. And delta T. So the mass hasn't changed, so that's still just equal to 100. C sub P is something that's tabulated. This is the one that you're most likely to end up accidentally memorizing. It's a good one to know. There's a lot of liquid water on the planet. It has a lot to do with, I don't know, temperature and stuff like that and climate change. So it's a good one to know. But yeah, 4.18 joules per gram degree Celsius. And then we're just looking at the change in temperature. So now that we're in the phase, since we know we're going through the entire phase transition here, we know our final temperature here is going to be 100 degrees Celsius. And our initial temperature is going to be 0 degrees Celsius. And then we just go through and we calculate that and we get some number out of it. Okay, but the calculation is basically identical to what we did in 1. The only thing that changes, of course, is that the heat capacity of liquid water is different, and also the range of temperature that your liquid over is going to be different than the range of temperature that you're solid over. But you can see it's the same thing. So let's see what we can keep going. Yeah, when we get to 4, now we're looking at a phase transition. So we're at 100 degrees, so we know we're going through boiling. And so we're just going to use the delta H of vaporization, multiplied in this case times the mass. So remember up here we're using mass, not the number of moles. 2,230 grams. And we're multiplying that times 100 grams, and the grams cancels out, and so you end up with this. Reasonably large number, 223,000 joules, or 223 kilojoules. And that is the energy associated with process 4. And then finally, let's see, for this last process here, process 5, we do one last calculation. Only now we're going to use, let me zoom in. Only now we're going to use the heat capacity for whatever the gas is. Which is 1.86 joules per gram degree Celsius. And then delta T remember that it's just somewhat arbitrary. I said in the problem that we were going to go up to 150 degrees Celsius for steam. It could be any kind of temperature, really. Any temperature of the boiling point, unless it's like an obscene temperature, you're just going to be in steam. There's no other phase transitions after that. And we subtract that from the boiling point for the last leg there. Yeah, and then you get some number out of this as well. And so now I've calculated the heat associated with each leg of this process. I'm going to zoom out a little bit here. I've calculated the heat associated with each leg of this process. And then when I want to actually sort of do the overall calculation, so remember the question, if we go back up here, is how much heat is required to take a negative 20 degrees Celsius ice cube that weighs 100 grams and convert it to steam. There it says steam, that's 150 degrees Celsius. And so in order to do this, you just have to, every time you go through a phase transition, you have to kind of break up the calculation. So if I'm ice versus liquid, those are two different calculations, and then I have to worry about the calculation for actually going through that phase transition. And in the end, I calculate a Q that's associated with each step, and then I just kind of sum these up. So I would take Q1 plus Q2 plus Q3 plus Q4 plus Q5. I meant to put those as subscripts, but then they're kind of big. But this Q, we call this like Q total, is a total amount of heat required to take it. Oh, good, I even have a total. 9,300. You guys feel pretty good about that? 9,300, really? 9,300. What's the units on that? Oh, no, okay, there we go. That makes more sense. 300. Okay, now I got different answers here. Now you guys are making me think I have to go through the calculations. Okay, good. I'm getting some consensus here. If you're getting a different number, so if you're understanding what's going on but just getting a different number, there's some, oh, no, 9,300 is for 5, actually. Yeah, so once you sum these up, Q total equals, yeah, somebody put it in kilojoules, which I like. Well, since we're doing them all in joules, I'll write that out too. 311,680 joules, which is, somewhere around 311 if we're just kind of rounding kilojoules. Again, you'll notice I'm not worried about significant figures here. I'm just kind of jumping around with them. If you want to learn about significant figures, go ahead and read them. The main thing here that we're trying to figure out is just how to do these calculations and not get bogged down with significant figures. But yeah, so that's how you do this, right? I think about all I'm trying to do. I'm saying, essentially, the calculation is saying, okay, I'm taking an ice cube and I'm heating it up and I'm turning it into steam, and I know the temperature change across that, and I know the mass of the amount of ice I have there, and I want to know how much heat it's going to take. Answers do not always have to be in kilojoules. It's just more convenient because it's easier to say 311 kilojoules than 311,680 joules. That's all. The answers are in whatever they end up being in. Usually, you try to use something that gives you like a manageable number. On the exams, you don't have to apply significant figures. They're multiple choice. I'm trying to think, like, we'll probably apply significant figures on our end, but if you're off by a little bit, it's not like we're going to have, 4 answers that are like super close together, where if like you messed up your significant figures somewhere, it's going to be some trick or trap that gets you. That's not what we're looking to do to you guys. So I guess significant figures are not crucial in doing this. But yeah, so that's how you do these types of problems. It's breaking them up, and it's using these same little equations over and over again. I'm trying to think of another good example. Oh, we got 10 minutes left. Yeah, I think let me think. I like there's other problems you can work like this that are kind of fun, although harder, where you take like you take like an ice cube and you put it in a glass of water and you let them come to thermal equilibrium. I don't know that I've ever given one of those on an exam, so maybe they're not super useful. They are kind of fun though. I think about them a lot. Uh, my son is obsessed with, like, there's a pool where I live, and my son is obsessed with taking ice cubes and throwing them in the pool. And I always think about, what the temperature changes for the pool from adding a single ice cube to it. You can actually work that out using this type of machinery that we just learned, but it's a little bit of a pain in the ass, and I doubt we'd give you one of those in the test because they're kind of long. Let's take a look at another thing. So like just a really quick problem. So once you get this down, it's not that bad to kind of run through the calculations. Usually the problems are not. I don't know that we take you all the way through because you can see it. Even though it's not super challenging to do the calculations, it can get kind of long. So usually I don't think we take you through like 5 phase changes or 5 different calculations or something on an exam. Usually it's more like 2 or something. We can think about the opposite. Let's say you have steam that's at 180 degrees Celsius. I'll show you how you can use steam is cooled to, and we'll stick with, we'll do 10 grams. 10 grams of 180 degrees steam is cooled to 45 degrees Celsius. How much heat? I guess I'll say how much heat is associated with the process. Okay, so is heat being... Okay, oh, there's a problem on one of the worksheets like that. Okay, well, we can work through one of those in office hours or something. We don't have enough time to kind of go through it. Those problems are fun. If you can work through the problems, I'm sorry, I'm jumping into the chat thing. If you can work through the problem where you have like an ice cube or some like 2 different phases and they come in contact with one another, and they reach the same temperature, you're doing well. Those problems are reasonably challenging, but they're hardwired into the mechanics of or the machinery that we just learned. But they can be a little bit tricky to think about, mostly in the sense that the phase transitions are something you have to pay attention to. Maybe we can work through one of those in office hours or something though. But yeah, if you've got 10 grams of 180 degree steams and it's cooled to 45 degrees, how much heat is associated with the process? So is heat being released or consumed when I go from steam to 45 degrees? I guess it's pretty obvious that the temperature is going down, right? So if the temperature is moving down, we're obviously going to release heat. So this is an exothermic process, and if you have that little, there's a nice little like thing in one of the LEs that has like a gas, has little equilibrium atoms, arrows or whatever, liquid, etc. Go look in LE1 or whatever, and it's in there. You'll see that it kind of gives you the signs associated with it. So for this one, since we're cooling, we know that delta H is going to be negative. But now that we kind of understand this, we can run through this pretty quick. We know that for 180 degrees Celsius steam, what's going to happen is it's going to cool to 100 degrees Celsius. And then at 100 degrees Celsius, it's going to go through a phase transition where it's going to go through and then when I go from 100 degrees Celsius to 45 degrees Celsius, I'm just, cooling liquid water. So here we're in the liquid state, here we're in the gas state. And then the calculation that you'd end up doing for this is Q is equal to N, the same thing. Q is equal. Let me use numbers again, I kind of like that. So I've got these 3 chunks here. And then for 1, we'd use Q is going to be equal to M times C sub P for the gas, because we're starting in a different spot now, and that's times delta T. And then for here, this is the main reason I want to work this out, is we're looking at condensation here. So like, let's say that, go back up and steal this. Not what I want. This is what I want. Let's say that, like, you're given this, right? And you're like, okay, well, I've got delta H of fusion, I've got delta H of vaporization, I'm even giving delta H of freezing here. You don't necessarily need to have the delta H associated with condensation if you have the delta H that's associated with vaporization, because they're going to have the same magnitude, they're just going to have opposite signs. So Q for this one would be equal to M times delta H of condensation times sorry, there is no delta T there because we're at the phase transition. To make sure we have them all there, this would just again be equal to C sub P times the liquid times delta T. But yeah, delta H, the main thing here is that delta H of condensation equals the negative of delta H of vaporization. And this should make sense, right? Because delta H of vaporization is 334 joules per gram. So this is positive for endothermic. And if you think about it, it should be an endothermic process because it's going to take heat to take liquid water and convert it into steam. That process is like reasonably easy to think about because you're used to putting a pot. You like literally apply heat to something to boil it. When you're putting something in the freezer or something to cool it, it's like, I don't know, at least for me, it's harder to think about what's going on because you're not involved with the heat exchange in the same way. But you are losing heat energy as something cools. So delta H of condensation is in fact negative. So negative 334 joules per gram equals delta H of condensation. And that's an exothermic process. And the same is, I don't know that we have any problems for it, but the same is true for delta S for all these different things. If delta S is like, let's say it's in going from vapor to liquid, delta S for that process, so it's going to be negative. In the opposite direction, it's going to be positive, but they're going to be the same magnitude, right? And then ultimately for this process, whatever Q total is equal to, which I'll leave as an exercise for you guys, would just be equal to Q1 plus Q2 plus Q3. So yeah, so practice that. If you need the answer for it or something, ask on Piazza. I'm sure somebody can throw up the actual numerical answer for it. The more important thing to learn here, though, is the process for going between phases and how to sum the Q up. So you look at Q for each individual piece, and then you just add them up at the end. Okay? If you look at the lectures, or even for our last class, and you start to actually really think about this stuff and sort of like try to get a deep conceptual understanding of it, you realize that, or at least for me, I quickly realized that like it's reasonably complicated to tie what's happening quantitatively to a microscopic picture of this. And we do a little bit of that. There's the expectation that you'll be able to do a little bit of that for the exam, but yeah, this is, I think, the real hardware that you typically learn, and it should just be, yeah. So I'm looking at the chat conversation. Looks like you guys are going back and forth on the numbers. Also, if I just make a mistake or something on my calculations, just that happens sometimes. You just have to let me know, and we'll correct that on Piazza or something. But anyway, this is how you work these heat curve problems. They're long. There's like, you have to kind of think about them really carefully. but they're not. I don't want to say they're not bad, because if you're struggling with them, that then that kind of stings. But they're not as bad as they could be. They're not as bad. I think they're not as bad as they seem at first glance, and it's kind of a cool thing to be able to do. All right, I'm gonna take a 8-minute break real quick so my voice can get a rest, um, and then we'll pick up in how long will we get on test? I think I said that somewhere. I'm sorry about the test. I'm really not trying to drag my feet in. I'm trying to coordinate with the other instructor. I'm not sure I'm going to be able to, but I think we give you guys 2.5 hours on exams, and these are better questions for office hours or Piazza. But we think we give you guys like a lot of time on the exam, and it's really only meant to be a 90-minute one. Yeah, let's go. Somebody's asking if we'll solve the liquid water with ice during office hours today, and the answer is yes. Let's do that in office hours today. I don't record office hours just 'cause I already have so much stuff I'm recording and uploading. Um, I guess I could. Yeah, I guess there's really no reason I can't just upload a second video when I upload this one. Yeah, I'll start recording office hours as well. Um, yeah, so I'll work through the liquid water pot. Yeah, you're welcome. I'll work through the liquid solid. They're coming to thermal equilibrium thing in office hours today, and then I'll upload that video. But yeah, if you're keeping up with working problems and you're kind of keeping up with this and trying to get, I know the lecturing, I don't like watching lectures. Like, that's just not how I learn. I tend to skim through text and then like ask people lots of questions. Um, so the lectures can be hard to get through, but they do contain most of the information that you need to solve these problems. I guess I like some video lectures. I shouldn't say that. But when I'm trying to learn something fast, I get kind of annoyed with it. Um, so anyway, I got to take a break, and then I will be back in this room, and we will work through whatever problem from whoever, somebody. Yeah, sorry if you have class, but you can watch the recording. And I think our TA has office hours today as well, and he's a physical chemist, so he should be excellent at this stuff. Anyway, all right, I'll see you guys in a little bit.